Hey guys, so I'm Charu Chandrasekaran and this is Marcello Maggioni. And today here we're to talk about the Apple LLVM GPU compiler. So here's the agenda for today's talk. First we'll talk to you about how Apple uses LLVM to build a GPU compiler. Then we'll look at some basics about the GPU, particularly what factors affect the performance of a GPU. Then we'll look at the actual GPU compiler, specifically what pipeline passes we use, and what challenges we faced while building the compiler. So here's how Apple uses LLVM. We live on trunk and we merge continuously. By doing so, we benefit from all the latest improvements that's done on trunk. This also helps us identify regressions pretty quickly and we can report them back. We try to minimize any changes we make to the open source LLVM code, and we try to reuse as much as possible. So here's how we do continuous integration. So if the green line represents the progression in LLVM trunk and the orange line represents the progression in our GPU compiler, year one we create a production branch. We merge from trunk to the GPU compiler, and any changes that is done in the production branch is merged back to the GPU compiler. As the branches progress, we continuously merge. So every year we create a new production branch from the main GPU compiler. But as we merge LLVM trunk to the GPU compiler, our production branches stay in very close sync to LLVM trunk. We would all like to minimize bugs and identify them as early as possible. For this purpose, we do regression testing across all our branches. We do register count and instruction count regression testing. We use file check across a lot of places in our compiler to verify correctness. Compile time and compiler size is regression tested, and even runtime performance is regression tested. Let's look at a quick overview of the GPU software stack. So here's an app. The user interacts with the app, and this chooses which shaders need to be compiled. So the app and the shaders are written using Metal programming language. Metal is a low-level programming interface that gives the user low overhead access to the GPU. You can write GPU graphics and compute workloads using Metal. So here's an app, and in order to compile the shader, the app needs to interact with the Metal front end and the GPU driver. The driver here is the user mode driver, and each app does this interaction in its own app process. The app sends the shaders to the driver for compilation. So here's our Metal shader. To get the shader compiled, the GPU driver calls the Metal front end in an XPC service. And an XPC service is an inter-process communication mechanism. The idea is that you want to restructure your application into a main process and a bunch of XPC services, so that even if your XPC service crashes or is compromised, the main app can continue to work. This helps improve reliability and security of your main application. So let's get back to the Metal shader. The Metal shader is sent by the driver to the Metal front end. The Metal front end compiles it and generates IR. The IR is sent back to the driver. At this point, the driver calls the backend, also in an XPC service. The driver then sends the generated IR along with some state information to the backend. The backend compiles it and produces object code. The object code is sent back to the driver. And finally, the driver generates the executable. The executable is run, and the user gets back his results. Now let's look at some basics about the GPU. So GPUs are massively parallel vector processors. Threads are grouped together and executed on SIMD lanes in a lockstep. And the threads that are in lockstep share a program counter. So here in our example, we have a 8-wide SIMD GPU shader core. We have one thread running on each SIMD lane, and they share the program counter that's shown. In a typical GPU programming model, the user writes code as if it's to be executed on a single-threaded CPU machine, like the function calls, the control flow, etc. There is no explicit vectorization of the operation. The code is just run in an implicitly parallel way. Let's look at that with an example. So here's a GPU kernel. It takes two floats, A and B, adds them up, and returns a float C. Returns a float, which is the result of C here. If this were to be run on our 8-wide SIMD GPU, then because of the implicit parallelism, the input and the output would become a float 8 as opposed to just a float. Let's understand latency hiding on a GPU. As seen in the image, multiple groups of thread are resident on the GPU at the same time to help with latency hiding. Most modern GPUs employ a mix of multi-threading and instruction-level parallelism to attain maximum performance. Let's understand latency hiding again with an example. So here's a GPU kernel, and let's assume that all the threads that are running on the GPU are going to be executing this kernel. So here's how the execution proceeds. The first thread in each SIMD lane that's marked red are grouped together, and they start executing the kernel. The first instruction in the kernel is a texture fetch. They all execute the texture fetch. On most GPUs, texture fetches have long latencies of hundreds of cycles. So once the threads issue the texture fetch, they continue executing the math instructions that follow the texture fetch till they reach the point wherein they need to compute this float 4D. At this point, they need the results of the texture fetch, and they are stalled. At this point, they are swapped out, and the second thread in each SIMD lane is grouped, and they start executing. They get scheduled on the GPU, and they start executing the kernel. They execute the texture fetch, continue execution, till they reach the point wherein they are stalled on the results of the texture fetch. At this point, they are swapped out, and thread 3 in each lane is scheduled. When thread 3 is stalled, thread 4 gets scheduled. Finally, when the fourth group of threads gets stalled, they are swapped out. And at this point, the first thread group that was initially swapped out is scheduled back in again. And this time around, we hope that the results of the texture fetch are available so that the first threads can continue executing the kernel without having to wait. In this way, the GPU hides latency by swapping between various thread groups. Let's look at the register file with respect to the GPU. There are a lot of threads that are alive, and they share the same memory backing the register file. In this case, there are 32 threads that are active on the GPU. At any point of time, there is only a single thread that is run on the SIMD lane. But we have to keep the state alive for all the threads that are running on the GPU in the register file to enable quick context switching between them. So if this pink box at the bottom, which is now going to jiggle, is the size of the register used per thread, then we need 32x that size to keep the state alive for all the threads that are running in the GPU. So you can see that for the 4 threads in the SIMD lane, it's marked A, B, C, and D. The other thing that I'd like to mention here is that register file is in general pretty far away from the ALUs, and accessing it consumes a lot of power each time. So if the size of the register usage per thread increases, so you can see that the pink box has increased, the size has increased, then we have to decrease the number of threads that are resident on the GPU so that the registers for all the active threads can fit into the register file. The most important thing that we want to bring out here is decreasing occupancy is going to impact latency hiding. You don't have multiple threads on each SIMD lane to context switch and hide latency. So, and if you can't hide latency, you're impacting performance. Let's understand spilling in terms of the GPU. So we have this huge register file, which is used by many concurrent threads that are running on the GPU at the same time. If the threads must spill data because they're all executing the same kernel, then we end up in a situation where all of them end up spilling at the same time. And this puts a lot of pressure on the memory and the caches because they're all trying to access the memory and caches at the same time. Let's understand spilling with an example. So let's assume we have a GPU that has 1024 threads running concurrently. This is more like a real-world GPU as opposed to our 32-thread example. And if all these threads are trying to spill exactly one 32-bit register, then we actually end up spilling 4 kilobytes of data because there are so many threads. And due to this, the L1 cache can fill up pretty quickly, even at very low levels of spilling. and hence typically spilling is very expensive on GPUs and should be avoided at all costs. The thing to remember here is that we don't want to be trading occupancy for spilling in a GPU. Marcello will now talk about the GPU pipeline.
Thank you, Charu. So our pipeline is a custom pipeline. It's different from the standard pipeline that you have in Clang, for example, and is very geared toward compile time because we are a JIT compiler, or we actually compile in memory when the execution of the kernel happens. So we need to be fast, and so we tune our pipeline such that it gives the best results with the least amount of wasted compile time. So let's go deeper into our pipeline structure. So when the IR comes from the driver unoptimized, it comes into a single module where all the functions that are going to be seen are visible in this module. It's like an LTO module. Our first step is to inline the functions inside the main kernel. We support function calls in our compiler, and we try to exploit them for getting better performance. But typically, GPUs use to inline most of the code because function calls have costs, like they have branches. They have prologues and epilogues on function. They can generate the saving and reloading of registers that uses the stack. As Charu mentioned, it's very expensive. So inlining most of the code is like the most safe solution usually. Recently, GPUs started to see more and more diverse workloads, and we have a lot of shaders that have relatively big functions that are called multiple times. So inlining all of them would actually trash the iCache. So we don't want that. So we actually we exploit not inlining the functions in order to avoid that, and we have pretty good iCache savings thanks to that. So let's see how we do our inlining. So first we run dead argument elimination because we want to get rid of all the dead arguments that could be generated, for example, by automatic tools that generate the code. We sometimes see some of those, or even like maybe bad programming practices. And then we do argument promotion. We do this before inlining because we want to, so argument promotion as like a little bit of explanation. Like that basically makes sure that you don't pass a reference to a function, but you pass, if you can load it, the values that is if the function loads only the value, it doesn't write to it, basically it promotes it. It basically does the load before calling the function and passes the value to the function. So we don't want to escape pointers because we can oftentimes avoid memory accesses through some optimizations, in particular to the stack memory or a kind of memory called constant memory, which is a kind of memory that basically is the content is the same for all the threads in that are running. Because of this, we don't want to escape the pointers, and we want to, when we inline, we want to see that if a pointer is escaped, we want to inline that function 100%. So we do this before. In Clang, usually is done after inlining. So just want to mention that. And then we proceed to the actual inlining. Our inlining decisions are based using the standard LLVM inlining policies, but we have our custom threshold that lean toward inlining more. And in addition, we have some constraints that basically if we detect certain condition, we want to force the inlining such that we avoid basically bad performance that could be generated. Like for example, in the case I said before, and I'm going to show soon, of escaping pointers and not being able to optimize away memory loads. So here is an example of what I was talking about. So memory accesses to the stack. If you escape the pointer, SROA cannot do its job of removing stack accesses. So we want to avoid escaping those, and we want also to avoid these constant pointers because we have this optimization called buffer preloading or also uniform hoisting that I'm going to talk about later. And we can oftentimes remove these memory accesses. So that's, we want to make sure that those are inlined. And we use IP array, interprocedural register location in LLVM, that's been recently added. Because when you call a function, it's very difficult to predict when it will cause a spill. Like, for example, in this case, we have R4 that is saved and reloaded around call site, because the register locator doesn't know what callee is using as registers. No, but IP array helps with that and makes performance much more predictable with function calls, because minimizes the risk of spilling, and we exploit actually IP array. I think without IP array, actually, we wouldn't have enabled like function calls in our compiler because of the risks. And then after relining, we run SROA. So SROA is very, very important for us, and we use it as a cleanup pass. So we run it multiple times in our pipeline. And we want to make sure that all the stack accesses, if possible, are removed. So SROA, whenever we think we clean up some stack accesses that by basically free them from certain ties that stops SROA from working, we run SROA so that we make sure that those get eliminated. And on the same page, we have some custom stack access optimizations that we do, try to remove as many as possible. Like one that I'm gonna explain now, that basically we do when we have small arrays that are accessed dynamically. We basically convert them into a series of select, and this allows us to getting rid of the stack access completely, and also the stack memory itself, because the array on the stack needs to be initialized, and that's very expensive for every thread. Imagine thousands of threads running, trying to write to memory and then loading back from it. So the least of this we see, the best. And then another very important phase for us is loop unrolling. So loop unrolling is important because branches are slow on GPUs, because branch prediction is pretty bad on most GPUs or inexistent. And also, like, the presence of loop can pessimize the quality of the code because it stops SROA from doing the job of removing stack accesses, for example, and also the scheduler, which is very important for us, and I'm going to talk about that later. The scheduler basically likes big blocks, and unrolling the loops gives the scheduler much more area to work on and do his job to make better latency hiding, essentially. So we have our own custom thresholds for inlining that are higher than typical GPUs, because we want to inline more. But if we detect, like in this case, that we could get rid of this stack access if we unroll the loop, we highly increase our thresholds even more to make sure that the loop gets unrolled and you get the code on the right. We need to be careful, though, because we need to be tracking register pressure very closely, because sometimes we have these loops with massive amount of texture fetches or memory accesses at the beginning of the loop that, if unrolled, they could create, because of our scheduler being very, very eager in trying to push memory accesses at the top so that they can start early and we can actually hide latency. Sometimes we end up in some situations where it's too eager in doing that and we blow the register pressure. So we need to be very careful in not unrolling these loops if we detect that we have a situation where we could blow the register pressure. So we avoid doing that to avoid catastrophic results. And we also employ partial unrolling because some loops are relatively big, but they have few memory latency hiding capability, opportunities, like in this case. So we unroll it partially in order to not blow the iCache, but and have enough latency hiding capabilities available. Another step we do is flattening the Contraflow. Normal code tends to be very branchy with a lot of small blocks that feed one another. And Contraflow can be expensive on GPUs because you need to set the execution masks for the various SIMD lanes to execute the various threads, and that is extra instructions. And also, like, small blocks hinder the scheduler work, so we prefer to merge them into the code on the right, so where we are basically speculating code and then selecting between the result. But our bet is that basically the better scheduler behavior, and the better scheduler behavior and the reduced amount of overhead improves the performance. Uniformity hoisting is another important optimization for us. Basically, shaders are meant to execute code across thousands of threads, but sometimes they have pieces of this code that executes the same, that produces the same results for every thread of the machine that is running on the machine. And ideally, we don't want to run this code thousands of times, no? But there could be pretty good reasons for why this code is present into the shader, because it could be difficult to hoist, or maybe even more expensive to hoist, because sometimes if you hoist it in the host code, and then you need to set the state every time you run the kernel. You need to change it, setting the uniform values, etc. So there might be really good reasons for why this code is in the shader. So what we do is we detect these patterns, like the one highlighted in red, where basically the initialization of the variable fvec is the same for every thread, because it's dependent only on constant things. And we detect these patterns and we transform it like this, where we basically hoist it into a separate kernel, where we do the computation. We store the result into this very fast memory that is often called uniform memory. It is very fast to access inside the main thread. And yeah, essentially in this kernel, this kernel runs only once, ideally, or at a lower rate. And we also hoist memory accesses in this separate kernel, like B and A in this case are memory accesses, and this is very, very important for us because we want to reduce the memory pressure in the main kernel that runs thousands of threads as much as we can. So saving even one instruction, it's actually saving from the main kernel, actually saves thousands or even millions sometimes of executions, depending on the size of the what the kernel is doing, essentially. Another thing we do in this stage is that if there are still some stack accesses around, like if there is, for example, this constant arrays that are not written to and are made of constant only, we move this to global memory, like this. So we make basically it a file scope constant. And this is much better because it avoids initialization, because this is initialized by the driver. And there's only one copy of this instead of one copy per thread. So less memory, better cache behavior, much better. And then we do CFG structurization. So Contraflow is tricky on GPUs because of how you need to handle the Contraflow masks. And some types of Contraflow are even more complicated to handle than some others. Like the one in this example, which looks very simple. It's actually relatively complicated because block C is controlled by two different blocks, A and B. So it's more difficult to set the execution masks for this kind of blocks because there's not only one dependency, one only block that deciding the fate of C. So a common solution to this problem for GPUs is to structurize the Counterflow. Our backend actually supports full execution of this kind of constructs, so there's no need for structurization at MI level, so at low level, at the latest level in the backend. And we also support things like loops with multiple exits and things like that. But we still actually sometimes do structurization because it can be because unstructured Contraflow introduces a slight overhead. So by structurizing the code, you can avoid this overhead. And so for small blocks, if C is small, we actually employ duplication, where basically we give to both the controlling block A and B a separate block C that gets executed and becomes much easier to set the execution masks for this, and it's cheaper at execution time. But the risk is that if the Contraflow diverges, you would end up executing code C 2 times, the block C 2 times. And that's why we do it only for small blocks. And also, typically GPU code doesn't diverge because that's not a good programming behavior for the programmer to do. So basically our bet is that the code doesn't diverge most of the time. So we thought about employing the LLVM structurized CFG pass, which is the open source pass, and we tried it. It worked, but it was increasing the register pressure for us in certain key cases, and it was generating more control instructions. So in the end, we decided to roll our own solution using actually duplication. So at this stage, we run also a bunch of other optimizations. So there's from the standard constant propagation to its combine, which we run as a cleanup pass multiple times in the pipeline. And also another very important pass for us is reassociate, which it's like key to us because most of our computation is floating point, and we have fast math on most of the times. And so we can do a mathematical reassociation, and that removes usually a lot of computation from shaders. And then we enter the backend, the actual backend, and we have instruction selection. So instruction selection is the single most expensive step in our pipeline, consuming 15 to 35% when we use selection DAG. Selection DAG is our main ISL. We have a lot of custom combines to try to exploit performance, folding operands, like operators inside of the operands of the instructions, like negations, absolutes, extensions, and things like that. So essentially, it's very important that we run all these optimizations. And for devices that are more expensive, that are less powerful, we have fast ISL. Fast ISL helps us keeping compile time in check, but is a pain to manage a separate path, and like moving all our optimizations into fast ISL, it's a pain. So our plan in the future, in the very near future, is to switch to global ISL, which is the new ISL for LLVM that our team is very, very invested into. We have a lot of people working on it, developing it actively, and I suggest if you are interested in global ISL to go and see the tutorial that other members of my team are doing later today. We hope the global ISL is going to give us a better performance and a better developer experience, where the developer is us in this case. Oh, sorry. And reduce the number of code gen prepare hacks that we have a lot in order to make selection DAG happy right now. And now scheduling. So scheduling is the single most important step in the pipeline for performance for us. So by scheduling the code right, basically we can avoid nasty pipeline bubbles, as you can imagine, but also improve latency hiding a lot. And also by forwarding between instructions the results. For us, it's very important because the register file, as Charu mentioned, is far away from the ALU and is expensive to actually power, to access it. And we are a mobile GPU, so by forwarding the results between instructions, we basically avoid having to round trip to the register file. So one of the main things we do, as I mentioned, is like moving stuff, like memory accesses up, so that we run them early, run independent operations in the middle, and then wait just before we need it. We need the results, and we need to be careful because we can exaggerate register pressure, and register pressure means less occupancy or spilling, which is terrible because it's both, no occupancy and memory access. So we also do like bunching texture fetches that access to the same texture together, so we run them together, and we are more likely to eat the texture cache. And also, like, we order memory loads by address so that we exploit coalescing of memory accesses. Then we do pretty standard scheduling with respect to like avoiding pipeline bubbles, but also keeping instruction results near to the uses so that basically we forward between instructions, and that's important for reducing the register file traffic. And another custom policy that is very important for us is trying to bunch operations of the same type together, because switching between different kind of instructions can be expensive for us. So we try to bunch, like for example, memory loads together with memory loads, or math with math, etc. We have many other custom scheduling policy. Our scheduler is huge, thousands of lines. And all these policies go one against each other, and they all go against register pressure. So we need to be very, very careful in balancing them out. And we spend a lot of time in scheduling. I'm going to mention it again later, but it's about 5 to 15% of our compile time. But it's very important, so we are very happy of doing it, essentially. Now I'll talk about some challenges that we experienced while developing our compiler with LLVM. So we are a JIT. We run runtime, so we care about compile time very much. And we spent a lot of time in tuning our pipeline actually to waste the least amount of compile time while getting the best results. And these are some of our main offenders with respect to compile time. As already mentioned, like selection DAG for us is 15 to 35% of compile time. Scheduling is another 5 to 15%. Instruction combining, 10%, and the register location is another 10%. There are also loop passes that sometimes are on this list and very prominent, but they're not always there. So these are the main offenders that are always there, and I'm mentioning this, but there are also loop passes sometimes for us are pretty expensive. And we have a custom pipeline, and we found different problems whenever we decided to run a pass in a different order with respect to what Clang or other more popular compilers do. So whenever we found such bugs, we had to fix them, and we did in open source. And another problem came from the fact that we reuse our one single compiler instance for multiple compilations, and we found different kinds of bugs that are very difficult to debug because they're data races essentially. Sometimes are like, another very common one was like cached results from a previous compilation that are reused in the next one, and of course if you do that, it's not good because you use data that is not the one of the current compilation. And we have to fix these problems also in open source. And another challenge we had was like designing our register file such that was actually acceptable. So basically, our GPUs tend to have instructions that accept a lot of data that usually is passed in consecutive registers. So you basically set up this data in consecutive register and you pass those registers to the instruction. And also there are instructions that produce data into these consecutive registers. We model this thing through register tuples. So our base register are the one at the top in yellow. And then we have these register tuples that are basically groupings of consecutive registers of different sizes. So for example, the one in green are register tuples of 2, where we have, for example, R0, R1 is a tuple, R1, R2 is a tuple, R2, R3 is a tuple, and so on. And the one in pink, R0, R1, R2, R3, R1, R2, R3, R4 are 4 wide tuples. And each of these tuples is a separate LLVM register that share the same register units. So basically, they share the same register units of the base yellow registers. And because we can go up to 16 wide of this, on some architecture, we can go up to 16 wide these registers, these are register tuples, we actually generate thousands of LLVM registers that all reuse the same register units. And this is very uncommon with respect to CPUs, where basically we have many more LLVM registers than actual register units. And because of this, algorithms that scale with the number of registers, or that basically iterate over all the register units contained in every register, they basically can take a hit because of this. So for example, we had a problem with the original IP array implementation because the function basically does basically determining if a function is using a certain, which register a function is using, which is one of the steps of IP array, was basically iterating over all the register and trying to find a register using the same register units as the register it was checking. And if it found one, it marked that register as used. And because we have so many registers and all the registers kind of like overlap with one another, we ended up having a near n square behavior that on the number of registers, that for us was disastrous. So we had to restructure the algorithm that basically worked very well for CPUs, actually, no problem, in order to have a better behavior for us, for GPUs, essentially. And then the last issue I want to bring up is like register pressure awareness, that for us is important. So LLVM has limited support for register pressure awareness. IR tends to ignore it. And machine level has some register pressure estimation, but most passes only care if they run out of register, while for us it's important also if we don't run out of register, but we increase the register pressure, so because of occupancy. So this is still an open problem for us, and we are tackling it right now. And before ending, I want to thank all the other members of my team that, I mean, we are only representing, and without them, all of this wouldn't be possible, so thanks.
Any questions?
I have a question. So you mentioned in your scheduler, you're trying to schedule node or texture fetch at the very beginning to hide latency. But as a consequence, it definitely will increase the register pressure, right? It will use more register. How do you balance that?
Yeah, that's very difficult. And it's one of the main problems that we have, essentially. Like, register pressure is very important for us, but latency hiding is also very important for us. So if you don't hide latency, you have more occupancy, and that's good. And because it can hide latency in another way, no? But if you don't do in-thread latency hiding, usually you don't have enough latency hiding in order to hide completely the latency. So we need to balance between the two. And we have many heuristics, and that's why our scheduler is so expensive, in trying to understand what is the current situation of the shader and try to balance things out. We also use sub-tree scheduling, which is a feature of the LLVM scheduler. I think few backends use it. We use the machine scheduler. I didn't mention it, but we use the machine scheduler, not the DAS scheduler. And with sub-tree scheduling, we basically, when we detect that the register pressure is high, we basically schedule sub-trees of code together so that we reduce the register pressure. And that's one of the tricks we use in order to keep the register pressure in checks. But sometimes we have catastrophic failures, yeah, and we get a bug report and we try to fix it.
Sorry, do you mind if I ask one more? Yeah, so sorry, I have another one. This thing is, you said when the register pressure is high, you will do something special like schedule the sub-tree, right? That's a good idea. But the thing is, when you found out the register pressure is high, it's probably too late. How do you address that?
Well, I mean, we have register pressure estimation inside the scheduler. So we basically try to understand, what happens if I schedule this, how much the register pressure is increasing, no? And we keep track of how much the register pressure, it's an estimation because it's before register allocation, but we usually get it pretty good, no? We don't do stuff like restart if we did a very bad thing, but usually we get it pretty good.
Okay, thank you.
Yeah, so my question is also register pressure related. So you mentioned in your architecture, you can basically trade occupancy by kind of increasing the number of registers per thread, right? So it means you actually have you can compile multiple copies of the kernel. So how do you know which one is optimal? Do you have like a heuristic kind of a priori, or do you pretty much always decide to compile for the highest number of threads first?
One answer, me.
Go ahead. I'm not sure I got it.
Okay. If I understood correctly, what you mean is that if we compile different, we decide, we compile different kernels depending on how many registers, we try to limit essentially how many registers the shader is compiling. Is that right?
Yeah, basically. So.
Okay. No, we don't. We compile the shader trying to get the best compromise, no? And our compromise is never spill. No, try to never spill. Okay. So even if you have to use all the registers that are available for one single thread, it's okay. But we don't want to spill. So because most of the time we get pretty good results by just compiling the shader with the the heuristics that basically generate what we think is the best result, no? And then we run it. And if we find cases where, oh wait, actually we are using too much registers, then maybe it's more of a global problem. We should never use that many registers we find this case, right? So we try to fix that. Our policy is not to try, like have different options, like try different settings and choose between the best. No? It's compile only once, try to tune the heuristics as good as you can in order to get the best result immediately. Like, also because we don't want to compile multiple times because we run a compile time. We run a runtime, so it's expensive. And we run on mobiles. So, thanks.
I had a non-technical question. So you mentioned that all of this GPU backend work is in a separate branch that's separate from the mainline trunk. But most of the issues you've talked about aren't specific to Apple GPUs. You know, they could be applicable to any GPU backend. How often do you try to release some of this work back to mainline, or is it all just in a private branch?
So we do merge our production branches very continuously back to the main GPU branch. So any changes that are done in our production branch is there for the future in our main branch.
Okay.
So it's like a continuous integration wherein LLVM trunk is merged to main branch and our production branch is merged to the GPU branch.
Okay, so all of this is available to other GPU backends as well?
No, if it's something custom to our target, then the main GPU branch that we're talking about is our main GPU branch, which is also local to us. But if there's any change we do to the LLVM open source code and we want to upstream it, we do upstream it back to the LLVM trunk.
Thank you.
So I have a question about the uniformity hoisting optimization. You showed a pretty simple example of like simple instructions. Is it actually beneficial for these kind of examples, or does it need to be heavier to offset the overhead of, you know, running additional kernel that basically stalls the execution of the rest of the kernels?
Yeah, so I guess the answer is that depends on what GPU you're running on. For our GPU, it's relatively cheap to do that. So even only hoisting a memory access for us is enough. Even only one add, actually. You hoist one add, it's good.
Okay. Additional question is, which point do you make this decision? Because if you have memory accesses and you're hoisting ALU instructions, there is a good chance that you will execute ALU instructions during the latency of the memory access.
You mean, what do you mean exactly? Sorry.
Yeah.
I mean that sometimes you can execute instructions that you would normally hoist for free because you will be waiting for memory access. Anyway.
Yeah, true. But I mean, the fact is that it's not only performance for us, it's also power. Like whenever you execute an instruction, thousands of times, you're reading the instruction, you're decoding it, you're passing it down to ALUs. That consumes a lot of power. So we prefer to hoist, even if it's not a performance benefit, because we would be waiting for memory anyway. That's good enough for us, because you save a lot of power anyway by not powering the ALUs and not powering the register file for all the threads and so on. Yeah.
Okay, thanks.
You mentioned that you reuse the same instance of the compiler for multiple excuse me, compilation cycles. Are you using a custom memory manager? Have you considered different approaches? Maybe garbage collection or just simple pool kind of allocation for performance or to reduce the memory leaks?
I think we use just what the standard, what LLVM is standard on that respect. Honestly, I'm not super expert on that area, so I would have to go and see. But I think we don't do anything special to try to be even more efficient on that perspective. So yeah.
Thank you.
Yeah, so no matter how much register sensitive heuristics or whatever techniques you use in scheduling to try to reduce register pressure, but still could happen. You cannot avoid spills. So I have two questions related to spills. The first is that for we usually have like 3 element vector and 4 element vectors, right? And then for you also represent this as a tuples of registers. And so in real programs, we might end up in a situation only one element needs to be spills. So in that case, how do you handle that? Do you want to spill the whole tuples or spill one element or 2 elements inside that?
Well, we want to spill as least as we can, and I think we do, actually.
I mean, do you use LLVM's mechanism to do that already?
Sorry?
I mean, do you use LLVM's mechanism to do that already, or you have your own?
No, we don't have our own. We
just use LLVM.
Yeah, just use what is there. And Matthias actually worked a lot on that, and thanks, Matthias.
We don't spill single elements of a tuple yet.
Yeah, we don't.
Okay.
It could be, but we have the liveness information, but no one implemented it to produce smaller spills right now.
Okay. So the other question is that when spill do happens, what's the time complexity to handle spills?
What do you mean by time complexity in the sense of runtime or compile time?
Compiler time. Yeah, compile time.
I mean, it's you are inserting extra instructions, and so yeah, that's the cost, but it's not particularly, compile time is not particularly a problem. The fact is that if you're spilling, probably you already have a pretty big shader that is doing a lot of things. So we never actually measured any compile time performance difference for us with respect to spilling and compile time. With runtime, yes. Compile time, no.
Okay. Thank you.
Thank you very much for the presentation. I think it's relevant for some other teams as well. What's the relative size, let's say, the difference between upstream and your private GPU compiler difference? And more importantly, though, as your private patch set grows, the cost increases because you constantly have to merge and refactor. If it's upstream, it's much more. The cost for you actually goes down. Could you comment on how you decide when to, maybe upstream a feature as opposed to keeping it private?
As far as possible, I think we try to upstream. We don't want to maintain anything. That's because merging, like you said, merging is an absolute pain, and having to do that continuously is not something we like to do. Most of our target-specific code is mostly is in a separate folder somewhere, so it doesn't kind of deal with what's in the LLVM open source. So that way we can keep sure we're not dealing with something that we have to merge constantly into that folder. Yes, we do deal with, if API changes, and sometimes we do deal with conflicts when you're trying to grab something from upstream, and it's something that we have to deal with, and we do. So I don't know if there is an easy way out, but our general rule of thumb is like, if you can upstream it, upstream it.
Yeah, I want to add that we have very little code in target, modifications to open source code that is not upstream. It's very little, in particular in instruction combining because of intrinsics and things like that. But,
One last question, maybe?
Sure. So I have a question now. So sometimes a few more registers doesn't necessarily cause your more threads to be generated. So how do you balance is you use enough the registers, but do not trigger the more threads the boundary. So it's kind of like a fine-grained local parallelism or the parallel of a threading level. Did you see my point?
So, no, we didn't
okay, so sometimes when you compile shader code, you use more registers. But because every shader, you need, for example, 5 registers. So if you use 6, you will not trigger the more threads. So maybe in this case, you could still use a few more registers without sacrificing the thread level parallelism. So how you actually manage this kind of fine level balance?
Yeah, so most of our policies are based on registry pressure in general. It's true, like you need to reach a certain threshold before you switch to like the next allocation block of registers. No? So we know how much is that, and some places in the compiler, I think in the scheduler also, I think, but I don't want to say things that are not true, so I will hold. We check that, and we actually say, oh, we have actually, we think that we still have a couple of extra registers, so let's use them, no, before we jump to the next allocation block. But most of the time, we just focus in trying to. We have a limit that we know if we go over that limit, it starts reducing the number of threads. No? So we basically hit that, no? And then we go in, oh wait, we need to be more careful and be more careful.
Okay, thanks.
Let's thank the speakers again.
Thank you.